Good morning, good afternoon, good evening to all those listening in on our latest version of Geek Speak. My name is Matt Burns. I'm the Technical Marketing Manager here at Samtech, and we look forward to spending time with all of our listeners over the next 60 minutes or so and the latest version of Geek Speak. Just a few housekeeping topics before we introduce a few people on the call with us. All of the presentation material will be available via email request and on our website, samtech.com/geekspeak. So please make sure to log on to that or email us at geekspeak@samtech.com with any questions that you have. We also operate on a question and answer throughout the presentation. So if you have any questions you'd like to ask to our presenter or our panelists, please submit those in the Q&A box, and we will try to answer those in real time. If we don't answer them in real time, we'll do that at the end of the presentation. And then any unanswered questions that we don't cover within the allotted time, you can submit to us again via geekspeak@samtech.com. Now that we have a few housekeeping topics out of the area, I would like to introduce my partner in crime and our continuing Geek Speaks webinar series, Scott McMurrow. Scott, how are you doing today?
Hi, Matt. I'm doing great now that I'm here. How are you?
Very good. Scott literally logged on about 2:14:58, so we're glad that he was able to join us at the last second. Scott, you want to introduce our speaker today?
Yes. Well, today our speaker is Gustavo Blondo, or Gus, as we generally know him. And Gus is here to talk to us today about DC blocking capacitors, whether they should go near the driver, the receiver, or somewhere else. And he mentions that there's a lot of confusion and even friendships have been broken due to this very argument. And I can attest to that. Gus and I argue all the time, and we've even argued on this topic. Turns out we were both right. Anyway, so Gus is a senior principal signal integrity architect at Samtech. In addition to his leadership roles, he's charged with the development of new signal integrity and power integrity methodologies, along with high-speed characterization tools and modeling. Gus has over 25 years of practical experience and a few more years of impractical experience in high-speed circuit design and has participated in numerous conference publications. Gus is a great teacher, and we're glad to have him here giving this presentation. Just a little bit of housekeeping. Remember to pose your questions during in the Q&A dialogue. We will open up Q&A at the end of the first of every meaningful slide where questions make sense besides the introductions and conclusions. And we'll I'll proctor that, and we'll attempt to answer all of those questions before the end of the presentation. Without further ado, I introduce Gus to you.
Thank you very much, Scott and Matt, for that great introduction. And thank you, everybody, for listening today. And without further ado, let's go into it, okay? So let me see if I can move this thing here. Okay. As Scott mentioned, okay, I see like a lot of confusion and a lot of like arguments about this, and I can totally understand those arguments because they are very logical. Okay, so in order to highlight that, what I'm going to do here, I am going to pose here the question as two persons. One is called Tim, referencing or a person that kind of like are more used to see life in the time domain. You can say like a traditional signal integrity engineer. And then you have another guy that I'm going to call Fred, with F for frequency, right? Which is more like an RF guy who is looking at the world more from like a frequency domain point of view. As you can see in the little picture in there, one guy is seeing like 4 logs, and the other guy is seeing 3 logs. So I'm going to basically pose the dilemma here with these 2 characters in the story, okay? And fundamentally the question, and the main question is like, should we put the capacitors close to the transmitter? Should we put the capacitor close to the receiver or somewhere else, okay? So in order to do that, I'll start with introducing some fundamental concepts about S parameters, more like a refresher for the people in the call, and I'll look a little bit in the time and the frequency domain. So that's going to be where I'm going to be posing the problem, okay? So then with that, I'm going to create very simple test structures, okay, to show who is right, okay, on, you know, or how to see the problem. And it's important to mention in here that this is really a fundamental principles presentation, okay? So one thing that I'm not going to be doing in here is really telling you what to do. I'm going to be trying, you know, to provide some of the tools and some of the ideas in order for you to perform the analysis and to understand what might be important and what might not be important. So a lot of the test cases and structures that I'm going to be showing are very simple structures that are not necessarily very practical in nature, but they are super useful to understand fundamental concepts, okay? And then after I show the test structures and we go through some examples of how things should be behaving, we're going to go and we're going to look a little bit more practical about those discontinuities, you know, how to simulate those discontinuities and, you know, what are important about those simulations. Again, I'm going to introduce a great paper that was published by a couple of friends of mine, and I'm going to mention those so that you can go and do further reading on it, okay? So that's kind of like the essence of the presentation that we're going to be talking today, okay? And finally, I'm going to go into the conclusion, since we're going to go back and forth into, you know, different topologies and different locations. I'm going to wrap it up in conclusions to try to bring it home, okay? So let's start with the topology. As I mentioned, this is going to be a very simple topology, and here I have it, okay? It's a transmission line that has a DC blocking capacitor somewhere in the transmission line, okay? This is a behavioral transmission line. It's a 50 ohm. The total length is 11 inches. In this particular picture, I have like 10 inches on the left and 1 inch on the right, okay? And this transmission line has all the natural behavior of the transmission line. Is causal, is passive, you know, frequency dependent, all that stuff, all that good stuff is included in here, okay? So now, to make it a little bit more interesting, I'm going to put like a little via at the driver or at one side. I'm going to put another via at the other side. And where we have like the DC blocking capacitor discontinuity, I'm going to have 2 little vias and the capacitor in the middle, okay? So now, again, when I am talking about these vias, for the moment, I really don't care too much about how the via looks like. What I am trying, you know, to highlight is the discontinuity. So, you know, right now I'm very simply representing these discontinuities with a capacitor, a 1-path capacitor, a 0.5-path capacitor, right? The DC blocking cap is going to be an RL inductance, okay, that represents the discontinuities as you go through. So we can think about it as a DC blocking capacitor, but, you know, at the end of the day, it's a discontinuity, okay? So now, then you see this red and this green in here, right? And this represents these S parameters, right? And the concept of symmetry and reciprocity, okay? So if you recall S parameters for a very simple situation like this, where we have only like 2 ports, port 1 and port 2, right? We have a 2x2 matrix, okay? S11 is what we refer, and S22 as we refer as return loss. S21 and S12 is what we refer as insertion loss, okay? And now we say like if S11 is equal to S22, that is when a circuit is symmetric. Okay, so the diagonal equality here is symmetry. Now, the off-diagonal S21 and S12 is when a circuit is reciprocal. Okay, in this particular case, this circuit is reciprocal, but it's not symmetrical. Okay, most passive elements that we work on in signal integrity in general are reciprocal, where S21 is equal to S12. But that's not a requirement. There are passive circuits that are not reciprocal. Okay, in this presentation, we're going to be talking about most of the cases where, in this case, they are reciprocal. Okay, but they are definitely not symmetrical. You see, the capacitor, for example, in this case, is much closer to the right than to the left. So if we look from this port, we're going to see something different than if we look from this port. Okay. Remember, S11 and S22 represents the reflections from port 1 or the reflections from port 2. Okay. So now, let's start talking about Tim, or the guy that looks at the work in the time domain. Okay. And this is his argument. Okay. Hey, you know, we definitely should put the capacitors close to the receiver. Okay. So why is that? Let's, for example, look at the red curve in here. What you're seeing in this curve is a TDR curve, time domain reflectometer. On the x-axis, you see time. On the y-axis, you see impedance, right? And all the little dips and wiggles in there represents reflections that you see from the port. Okay. So now, the red curve in here, or the orange curve, is when we are looking from port 2. Okay. And you can see, like, we drive our signal, we see like a huge capacitor or impedance discontinuity very close. It's reflecting a lot of energy, and then we go into the transmission line and we get into the other side, right? On the other hand, if we drive from port 1, is the blue line, you know, we don't see that big discontinuities, and when we get all the way to the other side, we are using to our advantage all the losses of the transmission line, and we have a much smaller reflection. So obviously, this person, right, Tim, is thinking, well, you know what? Definitely we need to put the capacitors close to the receiver, right? Because we're going to have much less reflections. We know, like, when we have reflections, all the energy that is reflected is not transmitted, right? And we want to transmit all the energy, okay? So it's a very reasonable assumption, okay? Another thing that I want to mention in here, before I go into, like, Fred's argument, is that, you see, with a single topology, this is important to understand, I can, without changing the topology, just by driving from port 1 or driving from port 2, I can put my capacitor at the receiver, or I can put my capacitor at the driver, right? If I'm driving from port 1, my capacitor is going to be close to the receiver. If I'm driving from port 2, my capacitor is going to be close to the driver. So without changing the topology, this is an important point that you have to remember in this talk. Without changing the topology, just by driving from one side or driving from the other side, I can place my capacitor either at the driver or at the receiver, okay? So now, this is the argument from Tim, okay? So then Fred comes along and basically says, you know what, Tim, you don't know what the hell you're talking about, okay? And he says, you know, these S parameters are all reciprocal, okay? So basically, the transfer from 1 to 2, S to 1, is equal as the transfer from 2 to 1, as you see in this S parameter frequency domain. In this case, we have, like, frequency on the x-axis, and we have dB or losses in the y-axis, right? And you can see they are on top of each other perfectly. So you see, it really doesn't matter where you put the capacitor, right? You can put the capacitor anywhere. Nevertheless, whether you drive from the right or from the left, they're going to be the same, because this is the transfer, and we represent transfer from one side to the other. You see, this is the interesting fact about this, right? So we have, like, two people in here, one thinking in the frequency domain, the other thinking in the time domain, that are making two very, very reasonable arguments, okay? Very reasonable arguments. So the question at the end of the day is who is right. So this is kind of like a paradox. Both cannot be right at the same time, okay? So before I leave this slide, I want to leave it with the reminder that here we are talking about reciprocal topologies, but not all passive topologies are reciprocal. I just want to make sure that's clear, okay? And in this particular case, this topology is certainly not symmetrical. Okay, so this is the problem. I'm going to pause, Scott, in case there's any question in here so far. Okay. So, okay, so who is right? Okay, so let's look at this a little bit differently now. So here is the same topology that I mentioned in the previous slide. It's an 11-inch topology with a capacitor 1 inch from the right. And here I'm going to put like a source with like a 50 ohm and a load also with like a 50 ohm. And I'm going to drive from this side and I'm going to see in port 2, or I'm going to drive from port 2 and I'm going to see my signal in port 1. And you know, we're going to forget about TDR and S parameters and all that. I want to just drive like a pulse from one port to the other, right? So at the end of the day, you know, when we are doing all our SerDes and all these things, right, you know, we are looking at voltage values and I's and things like that, right, so that we can represent with an impulse or a pulse response. So if we drive from port 1 and we observe at port 2 and we see a pulse response, and we see exactly the same pulse response as when we drive from port 2 and see the signal at port 1, we know like Fred was right, right? Because in theory, it should be much better for to drive from port 1 by team, okay? So now, notice a couple of things in here. I'm using exactly 50 ohms at the right and exactly 50 ohm at the left, okay? So now, I do the simulations and ba-bam, right? So we see like the pulse response is exactly identical, whether we drive from the right or we drive from the left, right? So ultimately, you know, this is automatically saying, well, you know what? Tim was wrong. Fred is the right guy in here, okay? So he was absolutely right. It really doesn't matter whether we put the capacitor on the RX or where we could put the capacitor on the TX. The signal looks the same, looks exactly the same. Now, the issue in here is like we can be very quick to assume that the location of the capacitor doesn't matter anywhere, or you can put the capacitor anywhere in the transmission line and it doesn't matter, you know. So let's do another experiment in here. Let's push it further. Let's do this experiment. Let's say I put my capacitor in here, and then I sweep this capacitor, right, or this discontinuity, if you wish, and I push it a little bit farther away in this direction, then a little bit farther away in this direction. So notice that what I am doing in here, and this is an important distinction that I want to make, I am changing my topology. You see, topology 1 is different than topology 2, and it's different than topology 3, right? Eventually, if I keep moving my capacitors all the way to the left, I'm going to reach a location of a capacitor here of the left that is going to be exactly the opposite of this, and it's going to be equal as this topology in here. But in any other location, the capacitor will create different topologies, okay? So now, if Fred is 100% right and say, you know, it doesn't really matter where the capacitor goes in the topology, that means that it doesn't matter where we put the capacitor, we should see always the same result from the right or from the left, right? Or, you know, but when we do that, we do not see that, okay? We do see, like, for different topologies, the location of the capacitor makes a difference, okay? And you can see here on the pulse response, this is a zoom-in version of the pulse response, and this is a zoom-out version where you see all these peaks and valleys and peaks and valleys, right? And you can see that you can almost identify by where those peaks are, where the discontinuities resides within the overall topology. This is due to halfway resonances that happens in here, something that I'm going to be talking quite extensively in my next geek talk in a month from now or so, okay? But you can definitely see that it's not the same putting the capacitor at 1 inch, at 2 inches, and 3 inches as this can be seen, okay? Yet, if I put this capacitor all the way here to the left, such len A is equal to len B and len B is equal to len A, this topology 1 is going to be equal to that other topology, which is equivalent of driving from the left or driving from the right, okay? So this is an important distinction to remember. So at the end of the day, Tim wasn't completely wrong, okay? You know, the location where you put the capacitor is important within the topology. It's not like you can put it anywhere. Now, the thing to remember is like when you pick the location of your capacitor, right? Whether you drive that topology from the right or from the left, you're going to get the same answer, okay? and that's really the rub in here, and that's what is sometimes a little bit confusing, okay? So for any given topology, same results are obtained driving from left or right. So in that case, Fred was right. But if we change the location of the capacitor, we can consider that as a different topology, and we have different sizes of half-wave resonances, and hence, Tim is also sort of right, okay? So that's why the two things are not necessarily excluding each other, okay?
All right, we have a few questions here. We actually have 4. I think one has already been asked, which is why is the topology changing? And that's to move the capacitor position with respect to the transmit and the receive end. So I'm going to answer that one myself here. Why is Fred not showing return loss in the previous slide?
Right. You know, that's a very excellent question, right? Because Fred is concerned about what I'm receiving from port 1 to port 2, okay? So I'm sending something on port 1. Whatever happened again back on port 1, I really don't care. I just want to see what I receive in port 2. And that is fundamentally insertion loss, right? And that's what you see in here, right?
Okay. Give an example of a passive topology that is not reciprocal.
A circulator topology, for example, would be a passive topology that is not reciprocal.
Okay. Okay, this question. If a TDR shows a reflection difference between port 1 and port 2, then I'd expect a pulse response to be different between port 1 and port 2. Why is it that they're the same?
Right. So that's exactly you know, the person who asked the question, that's exactly on Tim's camp. Okay. and yeah, you know, when you look in the time domain, you definitely feel that way. Okay. But it's really not the case, because at the end of the day, you're going to be losing that energy no matter what, where the capacitor is. You will see a little bit later. I think a little bit later that question was going to be answered better, because we are going to look at a formula, okay? And it's going to show the perfect symmetry of the formula, where you're going to see that as long as you have reflections, really the important thing is how much reflections you have at both ports, okay? And that is why it really doesn't matter that the reflections of port 2 is bigger than the reflections of port 1, because for transfer, the energy that you lose from port 1 and port 2 is taken away by the reflections at both port 1 and port 2. Okay, so that's really the answer for that.
Okay, there's a number of more questions coming in, but we'll go on to the next slide.
Very good, very good. Okay, so let's complicate things a little bit further. So now, you know, you can say, you know what, let's forget about all this mambo jumbo, you know, on looking at insertion loss and return loss, you know, and let's calculate the voltage transfer function. Okay, so this is the voltage transfer function, you know, and the moment that you do that, you realize, you know, in this equation, that this equation depends not only of the insertion loss, but also depends of return loss, and also depends on the reflection coefficients at the source, at the load, okay? So it depends of everything. So what is it then than, you know, having different return loss from the right or from the left? Doesn't matter. We'll talk about that in a moment, okay? So in here, I'm introducing two new nomenclature, you know, S11 and S22 and S21, we already know that, but then we have like this one, RS and RL. This is the reflection coefficient at the source. In our case, is either port 1 or port 2, and this is the reflection coefficient at the other side, okay, between the source or load impedance and the topology that you're driving. So now, here is related to the question that I was asked a moment ago. We have our beloved topology in here, okay? And as I mentioned before, I had 50 ohms on both sides, okay? But here I want to complicate things a little bit better. So, you know, well, maybe it's a little bit unfair. You know, we are not always going to have like 50 ohms on both sides. So let's drive port 1 with like an 80 ohm, and let's drive port 2 with like a 30 ohm. So you see we have like big reflections, you know, at this point, and we should have like big reflections on port 1 and port 2. And indeed, right, when we look at the return loss, we do see a very big difference between port 2 and between port 1, okay? So clearly there is big reflections. By the way, if I if I had the 50 ohms at the driver and the 50 ohms at the receiver, we would also see a difference in the return loss because the capacitor is much more closer to port 2 than to port 1. But here is exacerbating that a little bit further, okay? So now, okay, so we have this situation now. We're complicating things a little bit. We're changing the load and the source impedance. And again, let's do a pulse response, and let's see if the pulse response is the same. Oops. Okay, well, clearly the pulse response is not the same. And we say, okay, well, you know, things are different. But then you start looking a little bit closer, okay? You say, well, yeah, they are different, but they look awfully the same. You see like this edge in there. You see that other edge in there. You see these reflections in here. It's almost like this is an amplified version. The orange is an amplified version on the blue, right? And then you realize that in here, you have an 80 ohm driving a 50 ohm, so you have like a divider network, if you wish. And in here, you have a 30 ohm. So it's kind of like a gain somewhere in here, okay? There's some sort of a gain, okay? So let's look at that a little bit closer. Now, let's assume for a moment that we are looking at this at DC, okay? So let's say this is shorted. I know like we are trying to model here a DC blocking capacitor, but for the purpose of like high frequency, you know, for now we're going to assume like this is shorted, okay? So now, if we short this, right, we immediately realize that we have like a divider network, right? We have, for example, this source is driving through an 80 ohms into like a 30 ohms. And this source is driving a 30 ohm, an 80 ohm through a 30 ohms, right? So if I want to so clearly, right, in a situation like this, I'm going to have a difference in amplitude. The question is like, do I have something more than a difference in amplitude, okay? So what I'm going to do, I'm going to adjust the voltage in here to give it enough gain such the voltage that I'm exciting port 1 when I am driving from this side is exactly the same as the voltage that I'm going to be exciting port 2 when I am driving from the left, okay? And you can do that just following these simple equations. Right here I have my voltage on port 1 is Vs1 divided the addition of these two times 30 ohms. Voltage from port 2 is the same thing, Vs2 80 times 180, 110, right? And if I want Vp1 equal to Vp2, this is the equation basically. If I grab Vs2 or the Vs in this port and I give it a gain of 80 divided by 30, like this is going to be my Vs1 and this is going to be my Vs2. And what I am doing, simply what I am doing, I am guaranteeing that in here I am going to send the same amount of voltage that I am driving in here. Now the reflections are still very different, right? I have an 80 ohms to a 50, and here I have a 30 ohm to a 50. So it's very different. One is a positive reflection, the other is a negative reflection. Yet the amount of voltage, DC voltage, if you wish, that I'm going to be putting in here is exactly the same between port 1 and port 2. And the question is, again, when I do this, would these extra source and load reflections change the picture and make it look different whether I drive from port 1 or from port 2 when I have the right gain? And the answer is no. They look exactly the same. Again, I'm driving from port 1, I'm using this gain, And now I'm putting one on top of the other, and you can see that is exactly identical. So we started with a topology that has a capacitor on one side. Then we had like same load and source impedance. Everything looks the same. We went ahead and we complicated the circuit. We put different load and source impedances, so creating different reflections on the right and the left. And with the right gain, again, everything looks the same. And the question is why? Now, I mentioned that we're going to look a little bit at that formula, right? So now if you look at that formula, look at the beautiful symmetry of the formula, right? So first, we know that our circuit is reciprocal, right? So S21 is equal to S12. So, you know, we can keep here S21 whether we drive from port 1 or whether we drive from port 2, okay? So now look at the denominator in here, right? You see, we have a term that multiplied S11 by R source, which is this thing in here. And in the denominator, I also have S22 times RL. So you see, it's symmetrical. The denominator does not change. And it not only depends of S11, but also depends of S22. So again, going back to the initial question that person, because that question was very important because it kind of highlights the intention of the study here, right? So why, if from port 1 I have more reflections than from port 2, the voltage transfer function is the same? Because in the denominator of this equation, from a pure mathematical point of view, right, you are losing your energy on S11, and you're also losing your energy on S22. So no matter where you are, you're losing it both ways, okay? And this is the denominator. And on the numerator, this 1 minus and 1 plus represents the gain. That's what is going to give it the gain, okay? So now if you look at the frequency domain to please Fred a little bit more, here I am creating a kind of insertion loss, but not really. This is more like a voltage transfer function. And you can see that in voltage, the transfer function between port 1 and port 2, even on the condition where my source and my load impedance are different, the shape is pretty much the same. And the only thing that I do here, seeing here, is a little bit of a gain, okay? You can see when you're driving from 2, since I'm driving from 30 ohms to a 50, I have a little bit of a gain as compared when I'm driving from an 80 ohm to a 50, I have a little bit of a loss in there, okay? But the shape of the curve is identically the same, okay? So no matter what we do, right, we see like the location of the capacitor, as long as we are putting the capacitor symmetrically to the left or to the right, is going to look identically the same, okay? And that's what it's saying. The only thing that is different in here, we have to add a constant gain. Of course, right, if someone comes and say, well, you know what, but my source impedance is frequency dependent, well, that's a different problem, okay? It's a different problem. But in cases like simple real source and load impedance, you know, it's just a constant gain, and you get exactly the same result as shown here in the pulse response, okay? Any other questions, Scott?
Oh, we have a plethora of questions. This one from an anonymous character called Eric Bogan. He asks, how does the reflection from the capacitor heading to the transmitter get back to the receiver? So I think he's talking about the reflection off the blocking capacitor. How does that end up impacting the receiver?
Well, it will go back. It will reflect again, and it will go back. You know, so basically you have like two reflections going through here, right? But the same principle applies. Nothing is different, right? I'm going to drive my signal from here. I'm going to reflect. I'm going to come back. So now let me see if I can annotate something here. Where is my pencil? Just give me 1 second here. So I'm driving from here. Oh, I cannot annotate in here apparently. Wait. Oh, I cannot annotate. I'm sorry. So, okay. So I'm going to be driving from port 1, and imagine that you have like a little. Oh yeah, I am annotating actually, but the color is wrong. Just give me 1 second. I'm going to drive. Just draw the color. There you go. So I'm driving from here, right? I am hitting this point. Okay. Some energy is going to come back. Some energy is going to continue. Let's assume this is a lamp discontinuity, okay? So now, this energy that is coming back now, okay, so let's say green energy coming back, is going to hit this point. Now, let's assume in the initial case that this is perfect, and this is 50 ohms. Okay, at that moment, you know, this energy dies in here, right? Because there's no reflections coming back. But in this particular case, we have a via, we have different things. So now this reflection is going to come back in here, and it's going to go again, right? Eventually, this energy is going to hit in here, and the second reflection, a little bit more is going to be reflected, and a little bit is going to go further, right? But now, that is happening no matter what. And, you know, the same thing that happens with the first reflection will happen with the second, with the third, and with the fourth. And that's the way, you know, this is the way that happens, basically, okay? But you have to go through the whole topology again, and that is what is the same. And I think that's where Eric is going through, right? If your end point and your source point is the same point, that is a different thing. The key to remember in here is like the source and the destinations are different points. So no matter how much reflections you have to go through the same number of components and the same number of reflections, whether you go from the left or you go from the right, okay? In which case, the pulse response, no matter how many reflections you have, are going to be identical.
Right. It's like being a car on a bumpy road. Whether you go left to right or right to left, you're still going over the same bumps, and the same piece of the car still gets to the other end.
Now, let me say one more thing, Scott, and this is kind of like for the, you know, to incentivize the minds of the audience. Now, think what happens about crosstalk, okay, and try to come up with a conclusion. And think in terms of near-end crosstalk and far-end crosstalk, okay? And hopefully, you know, after the presentation, you will realize, you know, how can you understand that problem. Okay. Any other questions, Scott?
Yeah, there's a number of questions that I think we're going to defer to later. There are cases where people put capacitors near both the transmitter and the receiver. Does that even make sense?
You know, I do not know of a situation where that would make sense, but I don't want to say categorically that it doesn't make sense because I don't know all the applications. You know, in my experience, it doesn't really make sense to put capacitors at both ends, okay? There might be some other reason why you want to do that, but not from a signal integrity point of view.
Let's go ahead and go on.
Okay, very good. So let me back in here. Wait, clear all drawings. Undo this. Okay. Okay. So now, we've gone all over the place, right? Capacitors on the left, capacitors on the right, capacitors in the middle, capacitors everywhere. And one thing that we've concluded in here is like really, no matter where the capacitors are, both reflections at both ends are important and basically adds equally into the voltage transfer function equation, okay? So now the question is like, okay, if we have to find like a simple way to lower reflections simultaneously at both ends, that's the key, right? I mean, if I want to improve my transfer, I will have to reduce the reflection both at port 1 and at port 2, okay? How to do that? Okay, so now let's do like a little experiment, okay? So we're going to create the same topology that we've been talking about. We're going to have this capacitor, and we're going to move this capacitor from left to right and all that, right? We're going to put 200 femtofarad at both ends, which is a reasonable TX and RX die capacitance, right? Pump capacitance right there, okay? We're going to sweep the location of the DC blocking discontinuity, and we're going to compute both return loss, okay, on port 1 and on port 2. Now, here is the problem, right? When we're looking at return loss in the frequency domain, it's really difficult to say, you know, this return loss is better than this other return loss because we have a curve, and this is, and in general for return loss, we have a curve that is very peaky, right? It's like we have a curve that looks, you know, like this. So, you know, it's difficult to determine, okay, is this better than this, or, you know, whatever. So at the end of the day, it's more like an area under the curve type of a situation, okay? So, so what I'm going to do instead of like computing things in the frequency domain, I'm going to compute things in the time domain by using a methodology that is called effective return loss, okay? And you can imagine that as like almost like integrating the reflective energy coming to each port, okay? The good thing about it is like that give you like a nice number, and you know if it is a big number, that's good, that's very little reflection, okay? And if it is a low number, it's bigger reflection. So I'm going to grab that number at the left and at the right, and I'm going to add them, okay, in an RMS fashion, okay? So then
I'm going to add just one comment that
yep.
Effective return loss is a fairly new IEEE standard in the last several years. And another way to look at it, it is the effective return loss after equalization has been applied. So it is what's known as the reflections that cause unequalized intersymbol interference at the to the receiver. So that's important to remember, is that this includes the impact of equalization.
Right. Very good. Thank you for that comment, Scott. So, so we're going to do that. That's the idea. Okay. So now we're going to go and we're going to sweep this capacitor, and we're going to monitor this ERL. So when this curve is really high, we know that that's the best location for the capacitor, because that means less reflections. When this number is very small, we know that that's where we have a lot of reflections, and we don't want to put the capacitors necessarily in there. Okay. So before we go into like the fundamental curves, I'm going to show like an insertion loss plot. So in here, I am showing in blue the transmission line alone, nice, beautiful, uniform transmission line. Then the red represents a capacitor that is put 1 inch from one of the ends. And you can see the nice, well-developed reflections in there. And then the yellow is when the capacitor is put sort of in the middle. And you can see kind of like a noise ringing in there, okay? So the first thing that you realize, this goes back to, again, halfway resonances, okay? And, you know, when we put the capacitors at one end, basically what we are doing, we are colliding the two discontinuities at one end, and the halfway resonances that it's formed between these two ends is a much lower frequency, and that's what we can nicely see, right, the reflections in there. Now, when we put the capacitors in the center, we have two halfway resonances, but they are like much higher frequencies. Now, because they are at higher frequencies, we are using the natural losses of the transmission line that are attenuating it more, and that's why you see the resonances in there, but you see it in much more attenuated. Okay. So now, if I compute the reflections, you know, for every single location, not only at 1 inch at 5.25, but all across, okay, and I do that with an ERL with no equalization, okay, we can see that when we put the capacitor very close to one end or very close to the other end, is the worst spot to put it, right? As shown in the insertion loss plot, right? As we start moving the capacitors towards the center, the ERL gets better and better and better and better. When we reach the middle is where we have like the best location of the capacitor, because we are maximizing the uses of the losses of our transmission line and dividing the halfway resonance the most, right? And then as I go to the other side, it's exactly perfectly symmetrical, and I go to the other side, okay? So in this particular case, when we have an ERL, we know DFE, and that's what Scott was talking about. It's important to make that distinction, right? The center of the transmission line is the best location, okay? But, you know, that is a partial answer, okay? So, again, you know, don't take all this, you know, to the bank automatically, okay? It's just a partial answer. So now, what happens if we have an ERL with DFE? You know, we can create ERLs with DFE. Look at that, right? So now, what happens now? So we have the same behavior in the center of the transmission line, but now how much better now the return loss is at both ends. Why is that? Well, because the 12 taps DFE are acting, is long enough that is acting and is correcting the reflections that are happening both on the left and on the right. And you can see, like in this particular case, right? You know, you can put your capacitors also, it's pretty much almost as good to put the capacitors right at the very beginning or at the very end, okay? Because the DFE is fixing those reflections at the end. So the fundamental message that I want to convey out of this is like, you know, that's why I don't want to give you a solution. You know, I want you to give you like the tools for you to think about the solution. You know, the solution is really system dependent, because you can imagine, like in a real topology, you're going to have many more discontinuities than just a single capacitor. Okay, so you have to look at all those in order to determine, you know, perhaps the best location of the capacitor, right? But you know, but this will give you a little bit of an idea of how the trends, you know, what are you looking for, you know, how to think about it, and that's the goal. If I accomplish that, that'll be a great achievement here. Okay, that's the idea. Okay, so now I've driven you crazy, you know. Yep, sorry.
So let's stay on this, because this is a very rich slide. Well, so one question is, what is DFE?
I apologize for that. DFE stands for Digital Feedback Equalization. It's a type of equalization, okay, that normally, you know, we have at the receivers in SerDes, right? That looks at all the reflections, and that, you know, can almost measure those reflections and correct for it. Okay, you know, not go in so much detail. It's a type of equalization. Okay.
Now, I'm gonna mention one thing. If you look at these two curves, clearly, if you have more taps of DFE, the effective return loss is better, right? It's higher than the without DFE. And that's because DFE helps to fix a number of wiggles in the reflection profile. There was one question that unfortunately I clicked away, but the question was, how does DFE fix problems with the capacitor near the transmitter?
Right.
And so the question is, so if you could talk about how the DFE operates like a sliding window.
Right. Okay. So DFE has something that is called a reach of the DFE. Okay. So basically, it, you know, and that depends of the baud rate, or like the bit time. Okay, and the number of taps that you have in the DFE. Right. So for example, you know, you can have a DFE that is going to operate on a range of, let's say, I don't know, 200 picoseconds, for, to say something, right? So what is the meaning of that, right? So anything that is within 200 picoseconds of the peak of your impulse response is going to be corrected by the DFE, okay? So now, so that's a different topic, okay? But let me elaborate a little bit in here. Let's look at, for example, this case right here. Let me change the color in here. Change the color in here, right? So now, let's do this case in here. So, and let's say this capacitor, right? Let's say this capacitor, the length of this capacitor is 100 picoseconds, okay? It's 100 picoseconds. So if I were to do like a pulse response or an impulse response, I will see something like this, right? And I will see things like this, right? So now, this peak in here is due to the discontinuities between the beginning and the end of this capacitor, okay? And since, you know, it is 100 picosecond, is within the reach of the DFE, and it can correct for this. It can correct for this. But now look at all these wiggles in here. These wiggles here are much farther away from the pulse response, right? And that could be coming, for example, from the halfway resonance between the capacitor and this end capacitor and the discontinuity on DC blocking capacitor. Now, this is much lower frequency, is much farther away, so the DFE is not going to be able to reach that discontinuity, but it's going to be able to reach the discontinuity that is close to the pulse response on your driver. Okay, now The bigger the number of taps of DFEs, the bigger the reach of your DFE. Okay, that's what you know. But the more power your chip will consume as well. So it's a trade-off. Okay, and that's in this particular case, as we are getting really close to the driver or really close to the receiver, since I have like 12 taps DFE, the DFE is able to adjust for this, right? And as Scott is saying, it's removing all kinds of wiggles that is kind of like raising the whole curve, okay, as well. And I hope I answered that question that way. Anything else, Scott?
Yeah, DFE almost needs to be an entirely separate
that's right.
A presentation. It could take up easily an hour, but think of the DFE as a filter that is operating continuously, and it basically it's like this sort of sliding window, the sliding window being the number of taps. And any discontinuities that occur within the period of that sliding window get zeroed out. But anything that happens outside of that window, reflections, very, very long reflections, don't get zeroed out. And it takes actually a lot of thinking to really understand because it's beyond that. I guess we really can't say too much more. Let's go ahead to the next slide.
Okay, very good. So far we've gone about positions here and there. Now, one thing that is for sure, right, is like, well, if we forget about this position business, right, and we try to minimize discontinuities on the capacitors, that is really good, okay? So up to here, all the previous part of the presentation is more like theoretical, first principles, trying as best as I can to give you the tools to think about the problem. Now, this is where, in this slide, is a little bit more practical, and this is a paper that Scotty, a former co-worker, and Scott McMorrow here moderating, have created, and I have the link in a couple of pages later where you can go and read, and I will highly recommend you to read, that goes about how to model capacitors, right? Because, you know, and how to try to minimize those discontinuities. So in this particular case, we have like 3 situations in here. One situation, which is a capacitor with a void on the plane below, okay? And the capacitor is modeled just with a shorting bar, okay? They're calling this short void. By the way, I'm stealing all this from that paper, okay? So you will see all this in much greater detail when you go and you read that paper, okay? So the other one was modeling the complex void. You know, Scott and Scotty were crazy enough to go and model this capacitor, this multi-layer ceramic capacitor, adding all the different layers, interdigitated layers inside that capacitor, okay? So this is the more accurate representation of the capacitor. And this is kind of like a middle ground in between this and that, which is putting like a shorting bar on top of the capacitor, almost, if you wish, representing the first blade of that multi-layer ceramic capacitor, right? And they're going in here and they're trying to analyze how would this look for all these different cases, okay? So now, if I go into the curves, this is the TDR curves. Again, we have time on the x-axis and we have like impedance on the y-axis. We have like the orange curve, which is the complex solid. It's not represented in here, but you can imagine this case without a void. You know, so if you don't do a void, well, of course, right, you have a lot of excess capacitance between the pads and the first blade of the capacitor and the ground underneath, and you create like a big discontinuity deep in there, right? Now, if you go and you simulate this with like the short void, is this green curve, which is the more perhaps a little bit unrealistic case, is a more optimistic case, I would say, okay? If you go kind of like in the middle ground and you simulate it with the first blade of the capacitor, you see in here the, which one is it? This is the simple void, is the blue, okay? And then if you do the whole thing, which is this case, you will see what is the more realistic one, which is the red one, okay? And now you can clearly see that depending how much effort you want to put in simulation, right, which option are you going to look at? In the paper, one of the conclusions is like this is a reasonable, the simple void is a reasonable approach to take, you know, in order not to spend a lot of time simulator and getting you close in the ballpark. If you were to look at these pictures in the frequency domain, you will see, like, for the most part, this model capture all the resonances that this model has. Not exactly the same, but very, very close to it, okay? So it's a trade-off between computation time and simulation time and accuracy, okay? But the fundamental premise is like you need to look at things. You need to try to minimize those discontinuities, and you need to run some simulations to do it, okay? Another trick, okay, that I would like to propose in here to you is like, as I mentioned, you know, in the paper before this, I was doing very simple topology, but in reality, you have situations where your topology is much more complex. You have vias, you have connectors, you have all kinds of things. So, you know, you need to be opportunistic about what you do. For example, in here, I have a connector and I have some sort of a via. I might be able to put the capacitor really close to this connector and share a via, so I don't have to put two vias transition, right? So again, I am reducing the amount of discontinuities. I almost kind of like hiding the capacitor behind the connector, okay? So that's the goal in here. Think about your whole topology and where you can hide your cap as much as possible, and how can you share discontinuities to reduce ultimately the reflections caused by the discontinuities of the capacitor. Okay, so that's more like from a practical point of view. Any questions, Scott?
Yeah, well, I'm just going to point out, and we only have 4 minutes right now. We might run over just a little bit to everybody out there. These are already optimized capacitor transitions. Had we not optimized them, the TDR would have been about 60 ohms down. So this is just concerning how do you model it. And as you can see here, a good approximation is the green wiggle. Red is what actually is. Green is a good approximation, which is the short void across the pads. That gets you in the right ballpark for modeling, and if you don't want to model the capacitor itself. There were a couple of clarifications on dual. There was a clarification from somebody that reminded me that dual capacitors are used for safety, regulatory compliance and safety, because the DC blocking capacitor blocks inrush, low frequency inrush currents and DC currents from charges on the cables or charges on external circuits. And so it's not uncommon to put capacitors right at the connector or egress to the external world to keep that inrush from coming in. In that case, you just have to make sure that the capacitors are large enough so that the series capacitance still is in the range of your signaling pattern. One person mentions that, doesn't this mean that DC blocking capacitors at the center is the best bet without when there's no signal condition? And that's a good answer, is that the closer to the center of the channel you can get, the better off you're going to be if you don't have good equalization. So for example, PCI Express, many of the older PCI Express generations had very little equalization. So the best place to put your required transmitter on the TX side board is as close to the connector as possible, so that you maximize the distance away from the package. Although the connector itself becomes a reflecting item, so you might want to put it in between the two. Gus, we need to provide some references for both DFE, simple tutorial that might be available and searched for online, and also some papers on ERL, because there were several questions on, well, what is the equation for ERL? And unfortunately, it's not an equation. It's a convolutional process.
Absolutely. Isn't Rich going to be talking about ERL and COM at some point in this Geek Speaks?
He will be talking about COM. I don't think we have one on ERL. That's probably something that we should bring up.
Okay. Okay. Very good. Very good.
Question is, does a more typical 3 to 5 tap DFE also compensate for the capacitor reflection? It's a good question. Maybe we could. Go ahead.
I didn't hear the question. Can you ask the question again?
Oh, I'm sorry. I was turning my head away. Does a typical 3 to 5 tap DFE also compensate this much for the capacitor reflection?
Yeah, likely not. Okay, because remember, when we're talking about chips, again, it all depends of what is the baud rate or the bit rate that you are dealing with, okay? But I mean, in general, if we are talking about like high frequencies, 25 gig, 56, right? No, and the reason is because remember that normally, your DFE is on your chip, and your chip is in a package, right? And your package is like 30 millimeters away already, from your board, and then you have some half an inch or something before you get to your caps, right? So it's really farther away, than the reach of your DFE, right? Now, perhaps on a smaller switch chips or repeaters or CDRs or something like that, right? Where you have smaller packages and you have big number of DFEs, you will get to it. That would be my appreciation on that one.
Hey Scott and Gus, we appreciate the spirited conversation that we're having here and the great technical detail. But given that we're over time, can we wrap up with a summary slide, please?
Yes, sure, absolutely.
Thank you.
So let me conclude really quickly. Okay, in here, say voltage transfer function we're driven from either side, plus gain on a matched case, as I mentioned, 80 ohms versus 30 ohms example. Again, remember, look at your system, right, and figure out where you can put your capacitors so you share discontinuities and model things, okay? And remember that the capacitor location does matter, okay? And it generates different peaks depending of like half-wave resonances and amplitude of discontinuities, okay? So much more to talk about it, but I want to get into this slide. That is the paper that I was mentioning. And also, I published a few years ago an article related to this in the SIG that has a little bit more detail about different things, so you can go and take a look at it as well. Okay. Thank you, everybody, for listening.
All right, Gus, we appreciate the presentation. Very nice job. And again, as always with GeekSpeak, we appreciate the spirit and detailed questions from our listeners. Just as a reminder, if we didn't get to your question, please do submit it to us at geekspeak@samtech.com, and we'll try to get that answered as quickly as possible. For continuing questions about any signal integrity needs you have, please contact our signal integrity experts like Gus and Scott and the rest of our team at sig.samtech.com. We will have the recording posted on our website at samtech.com/geekspeak within 24 hours. And if you'd like the presentation, just drop us an email at geekspeak@samtech.com, and we'll get that to you. With that, we thank everybody, and we'll look forward to seeing everybody next week.